I would like to thank the organizer for giving this opportunity. And I'm an operator algebra, so for me it's quite unusual to talk about operator theory today. So it's an operator theory talk. So let me start with Witten index, what Witten defined. So I just give you the definition, but probably you guys know better. I think you guys are significant of this definition better than me as well. Probably you. So for positive number, so in the supersymmetric Hamiltonian, he defined the what we now call the Witten index by this formula. So it's a graded trace of e to the minus beta Hamiltonian. This is the definition of the index. And here, so H is a supersymmetric Hamiltonian and it's square of odd self-adjoint operator. So Q is of this form. So odd operator, so it is of this form, self-adjoint. So in terms of T, then this can be written as the following. Trace is beta T star T minus E to the minus beta T star. So mathematically, so this is what Witten defined. And let me talk about a very special case. Memory. So okay. So in order for this formula to make sense, then this difference should be in the trace class. But as this, for simplicity, let's assume that each term is in the trace class. Assume so both then make sense. Just for simplicity. Okay. So these are finite. Then so in the formula, so the contribution coming from the positive eigenspaces of T star T and T star, they cancel place. So what remains is the information of the ground state. So it turns out that so this is equal to, in this case, so the formula is equal to the dimension of the kernel of T minus the dimension kernel. So assume if this holds, then you get this kernel of T star. So this formula shows that this is nothing but the Fredholm index, the usual for the Fredholm index. Right? So in this sense, the Witten index is a generalization of the Fredholm index. Okay. But in general, so you don't assume that each term makes sense. But what you need to assume is that only this difference is in trace class. Right. So this count in the supersymmetric quantum field series. This counts for the number of the boson minus the number of the ground state. Right. So this is the original definition of Witten. Then now I'll talk about right. So mathematical work. Probably this work is not the first mathematical work, but I think this is the first systematic work of the mathematical stuff. This object, get Z and Barry Simon. It is in 87. So this is mathematics. So define this. I give you the precise mathematical definition. So the assumption is that T is a closed operator on a Hilbert plane. Yes, we define the closed operator, a Hilbert space. Okay, and assumption is that assume this difference belong to trace class. In my notation, this is the Schatten P class. So this is trace class. For large enough beta. So this is the assumption. And well, in the original Witten's definition, then you don't need to take, well, at least in this case, in this very special case, then you don't need to take limit when the beta goes to infinity. So the formula doesn't depend on the beta, at least in this, under this assumption. But well, in this generality, then so this number, so that if you take the trace, then the number actually depend on the beta. So they define the Witten index. So this is my notation for Witten index. So without W, it's just a Fredholm. Okay. So they first take the trace. And then take the limit to remove the beta dependence. But there is no guarantee for the existence of this limit, so if it exists. So this is their definition of the Witten index. And actually, there are a lot of work which compute this number for very concrete T, Dirac type operators. There are a lot of work. And actually, for concrete model, it's not so easy to compute this explicitly. It's a lot of hard work, usually. Right. And in their work, what they did is that, right, so let me go here. So in this paper, so not only they define the mathematical definition of the Witten index, they show, I think, three important things. They show, first of all, so if moreover, so T is Fredholm, so in addition to these assumptions, including the existence of limit, if T is Fredholm, then they turn out that the two indices coincide. So this is, so in this sense, it is really a generalization of the Fredholm index. Okay. And second, they show, so I don't want to be very precise, this passage, they show the so-called topological invariance. So in mathematical, it's invariance and the perturbation. But
is it multiplicative?
I don't know. Actually, in my examples, then it is. I mean, the class I work on, then it is multiplicative. It's a consequence of my formula. So they show the invariance and the perturbation. People say it's kind of a relatively trace class perturbation, but their definition is rather complicated, so I don't want to go into that. But I think in physics, it means that it's invariance. I think it's a topological invariance of the index.
But the perturbation, I guess, is small in some sense, right? I mean, it's
not relatively trace class. Relatively trace class, but if you look at the definition, then it's rather complicated. I mean, if you have a look at their paper.
You're saying that it's also stable for bounded perturbation, small part that
small part, yes, small. The sense, so the what subtle is what you mean by small. Yeah. But it's yes, so it's invariance and the perturbation.
In this case, in this first case, so this difference of traces is independent of beta, no? does not depend on beta.
Sorry?
So the difference, so you say it could depend on beta.
Yeah.
But in this case, it's not, so you don't have to take the limit or you have to take the limit.
So
So it's
in the Witten's definition, and if you have two terms, if each of the terms belong to the trace class, then doesn't depend on it.
Ah.
It gives a freedom of index, so it doesn't depend on beta.
okay.
Yeah.
So if more. If not, it would depend. But
For general case, and then it
it
does
depends.
actually it does depend on
The limit then gives the right index.
right.
Okay, thank you.
And the third thing is that they discuss the relationship of the definition to the or the client theory. It's a classical, so very nice theory over the theory, client theory on of so-called spectral shift function. Namely, so assume you are given two self-adjoint operators, not necessarily bounded. Self-adjoint, assume you are given two self-adjoint operators, and assume their difference is trace class. Although A and B might be unbounded, but you assume that the difference, so they have a common domain, and you get a trace class difference. Assume that. Okay. Okay. In this situation, so under this assumption, then you can see that there exists a unique relevant function. There exists a unique relevant function called the spectral shift function, depend on A and B. L1, such that, so you get this. For a large class of function, you do functional calculus, A and B are self-adjoint, you can do it. Then the trace of the difference of phi A and phi B can be calculated by this formula. So I should specify the class. Should I go this way? Probably. I think it's better. Yeah. Why is three? So here, the class of function is the following. Actually, it's not the optimal class, but I follow the Schmidt textbook. So the statement is this: for any function belong to this function space. This is a set of C1 function on the real line such that its derivative is a Fourier transform of a measure. So here mu is a complex measure.
That's complex measure always.
Complex measure is already
Okay.
has bounded variation, so it means that so the derivative is always bounded. It's a necessary condition. Yeah, at least in this class of function, then you guarantee that the difference is in the trace class and the trace formula holds. So this is a nice classical theory of Klein of spectral shift functions. And if you look at the definition here, then it's natural to apply the Klein theory. Namely, so assume the self-commutator is a trace class. Then you can apply the Klein formula. you can apply the Klein formula and then you get a delta t. Delta t. This you can compute this minus beta equal to minus beta x, and you need a spectral shift function of delta t and tt's. Right. So it's natural to use, from the definition, it's natural to use Klein theory. And actually what they did. And so if you take the limit when beta goes to infinity on the right hand side, then you, at least formally, you see that the Witten index of such t is given by I think a minus sign of the spectral shift function. When you assume if the this function is at the limit from right, then so this the limit actually exists, and you have this one. So the Witten index can be computed by using the spectral shift function. Where the problem is that in general, it's not so easy to compute spectral shift function for a given pair of self-adjoint operators. You have to compute the Fredholm determinant explicitly. But anyway, so this is such a beautiful format. And sometimes it is useful. Okay. Right. Oh yeah. So I should, probably better to generalize this, since we are only working on in my talk. So I'm only working on the bounded operators. So I don't really need a function on the R. So let me introduce the restricted version of this class of. This is a class function restricted to finite interval. So here, for later use, I introduce a point. This A be an interval. It could be a finite or infinite. It's a sub-interval R. Then I introduce this class of function. Okay. So this is a set of functions which is P1. That f extends to a function in WR. Which means that the class of function for which the Klein theory applies. And let me give you one example.
So you take bounded, you mean you take T bounded? So you take T bounded operator. That's now you said I'm working with bounded operator.
So I'm going to working on.
You are going.
For general theory, it's since I'm working on Toeplitz operator, so I'll concentrate on bounded operator later. Right, and I think there is a very instructive example. So example. So x to the p. So this belongs to this class. If and only p is less than larger than or equal to. Because its derivative should be bounded. It's clear. This condition is necessary, but actually using a Fourier transform or Fourier series, then actually you can show that when p is larger than or equal to 1, then this function belongs to t. You can apply the Klein. And if you are familiar with the theory of operator monotone function, then you realize that there is only very small overlap with the set of operator monotone function. Only constant function is in the intersection. So kind of opposite to the operator monotone function.
Operator convex though.
operator convex. Actually, so if I have enough time, then at the end of my talk, actually, I also talk about operator model function. But in that region, you cannot really use Klein theory. So you need a different technique.
And can you get the logarithm by some limiting procedure after your analysis?
Logarithms.
Out of from the boundary.
I think so.
Yeah.
I think so. Logarithm. Yes, it's operator monotone. You avoid zero.
Yeah.
But in that case, I talk about later. In that case, then you need to assume the good regularity of the thing. Right. And then next I'm talking about the Toeplitz operators. So so when you talk about the Fred-Hoff text, then I think best example is best example comes from Toeplitz operators. So it's very easy to analyze, but it's still non-trivial, and there are a lot of generalizations. So Toeplitz operator, the class of Toeplitz operator is my favorite example of a Fred-Hoff index. So from operators, so now I talk about Toeplitz operator. And to introduce it, then I need a hard space. So let me recall it. The hard space H2 on the circle is a closed subspace of L2 space on the circle. So the set of F, set of function F, such that the negative Fourier coefficient vanishes. All. So this is a closed subspace of L2 of T. And every function here, maybe think of the boundary value of analytic function on the disk. Okay? So you can also use the technique coming from the complex analysis theory of the disk space. Right. And so I introduce the hard least projection. So since this is a closed subspace, so there is an orthogonal projection. This is often called the least projection. Projection. Then a Toeplitz operator is with a symbol F. So F-O F. So I consider only bounded symbol, so it's an L infinity function on the circle. Then a Toeplitz operator F is defined by the compression of the multiplication operator. So on L2 of T's, and you have a multiplication operator of F. You compress it to the hard space, and you get a bounded operator. So this is the so-called Toeplitz operator. With symbol F. This is the definition. And this class of operators provide a very nice, example of a Fred-Hoff operator. My favorite example in my course of advanced functional analysis. So it is well known that if the base symbol is continuous and has no zero on the circle, okay, then it's known that the Toeplitz operator is Fred-Hoff. And moreover, there's a famous, Toeplitz index formula. You can compute the Fredholm index of Toeplitz operator, and it is given by well, it's a topological invariant. So minus times the winding number wave. So remember, so f is a continuous function from the unit circle to complex number, but it doesn't take zero. So the winding number makes sense. If you like, you can divide f by its absolute value, then it's a continuous map between S1. So winding number makes sense. And actually, the Toeplitz operator, index of Toeplitz, Fredholm index of Toeplitz operator is minus times winding number. So it's very easy to show it, but it's a kind of index cell. Analytic index can be computed by a topological index. So this is my favorite example. So then it's natural to generalize this formula to the Witten index. But for that, then I need more regularity. Here, I just assume that f is continuous, and that's not regular enough. So let's assume that so you can derive the integral. So assume, moreover, assume that f is absolutely continuous. So you can, so it's I use this notation because it is so it is a Sobolev space. So this is a set of absolutely continuous functions. So it's a bit smaller than T1, but well, essentially, so the distribution sense derivative is L1, so it's good enough. Then actually, so this you can write down the winding number by using integral. So probably you run this kind of formula in complex analysis. Okay? The winding number is by this form. Right. So this is a very nice integral formula. And now I can generalize this formula to the index. Namely, so let me write down my main result stage. So I don't want to be precise because there's a long assumption. It's nothing difficult, but just long assumption. So for a large class, for the large class of F, single F, the Witten index exists. And it is given by the same formula, except that the integral is a singular integral. So it is a principal value integral. So this is a principal value integral. It's no longer the ordinary integral, it's a kind of singular integral, but still you have this kind of winding number formula.
The singularity. So where is the single? So principal value with respect to some.
Actually, it's not really a singularity for F, but it's singularity for F inverse.
Okay.
So that means I allow F takes zeros on the side.
You have some zero and you
Yeah,
take the
otherwise you get a Fredholm formula.
but one or more. So
You receive that. And reason why I worked on this this formula is but just by chance I encountered the Matsuda Matsuda and other result. So they computed the Witten index of a Toeplitz operators. Actually, they are in that paper they are working on the so-called quantum walks. And as an invariant of quantum walks, they try to compute the Witten index of Toeplitz operator. And so but in a very small class way. Or some trigonometric polynomial, very small class. So they just use just try to compute the spectral shift function and they evaluate the index and they end up with a half integer. When it's spread from its integer, but in some parameter region, they got a half integer and they didn't know why half integer appeared. But now I can explain why you get half integer in there. Let me give you one very instructive example. So just consider rational function. That's enough. So let's consider rational functions. So it is R is rational, but we want to continuous symbol, so we don't want to pole on the circle, on the unit circle. So I assume that it is of this form, say, n that minus aj and equal 1 n minus c. There is no pole on the unit circle because I want to have a continuous function. So okay, this is a very nice C infinity function. But if there is a 0 on the unit circle, then it's not Fredholm. Okay. Because, well, the function is not embodied. There is a 0 on the circle. So you don't get Fredholm. It turned out that you can apply my formula for this class of function. So then the width index, this for this symbol. And now if you see with that formula, then if you get something familiar, you have looked in your functional complex analysis course. So namely, the formula you get is that 2 pi I. Let's see, the principal value integral, the unit size. And here you have a contribution from the poles, and the zeros. Right. So yes. So from the pole, then the only poles inside the disk contribute to this formula. So we get this which AJ where AJ inside the disk. I'm sorry, so I need multiplicity here. Okay. Oh, this is a contribution from the pole inside the disk. We also have a contribution from 0 inside the disk. MK, and we have a contribution from the zeros on the unit circle, and here you have this weight 1/2 because when you compute this principal value integral, then you get only 1/2 of the residue. So this way, so this, okay. So this is a precise form. So this explains why you get when your symbol has 0 on the unit circle.
You. No, you wrote that the absolute value of B is different from 1.
Yeah, so for poles, the contribution is only from the inside the circle, inside the circle. I mean the disk. But for zeros, then you allow F has a 0 on the unit circle. You have this term.
This is A.
Not equal to 1.
Sorry.
No, the top line.
No. 0.
That B by assumption.
Sorry about this confusion. This is B, A, and A. Yeah, I'm sorry about it. But I think in my paper there is no. This could explain how you get a half integer in the master data reserve. But actually, so you can relax the regularity a bit more. And so this is a nice infinity symbol, but sometimes you can relax the regularity of the symbol more, and you can consider similar but a bit different symbols, namely you can consider this symbol too. Namely, you have branching point on the circle. Alpha should be positive. Okay. So this is no longer C1. If alpha is less than 1, no longer C1. But this is good enough. And you can show that for this symbol, the Witten index exists. And the computation is the same. Exactly the same. So that means that you get, let's put the n here, and is an integer. Then what you get is this. So it means that, so this takes any real number, not only half the integer. So it's actually for physical model, it is known that the Witten index can take any real number, but so such an easy computation actually I should prove it again here. Right. So the point is that so you allow very mild singularity. It's a branching point. 5 minutes. Okay. Well, I should say something about operator monotone function for Stefan. But
I think you have a few more minutes.
I'm afraid I have no time because I should explain the formula behind this integral formula. I mean the theory behind this. It's just classical Helton-Hart formula. I use only the classical Helton-Hart. So for 5 minutes, probably I can explain it with that data. So that okay, Helton-Hart. So usually when you discuss the Helton-Hart formula for the trace, you only consider C infinity class function, but so for as that example suggests, so I need a symbol with lower regularity, so I need actually sovereign space. This sovereign space. So it's L2 satisfying this condition. I consider this solar space. Then actually it's easy to show that for any f and g in this intersection of this solar space and the set of absolutely continuous functions. In this class, then you can show that. So the commutator is always trace class. And the trace of the commutator is actually it is a famous Helton-Hart formula given by this integral. FDG. FT G prime T. So this is a famous Helton-Hart formula. It was known in the 70s. And so using the Helton-Hart formula, then actually, so the important thing is that this class of function is not only a linear space, but this is an algebra. So you can multiply functions here. And repeated use of Helton-Hart formula showed that we can get a more general form. Right. So the technical theorem is the following. So assume F is in this space, our working space. And assume that so phi belongs to this class of functions. The class of function for which the Klein theory works. Though I don't really need Klein theory, but I need this class of function. Then you can show that the difference is trace class. And the trace form. You can trace form. By using only the symbol. Pi, and what you get is a bit different from the formula you see in the Klein formula. In the Klein formula, you get a derivative of phi, but here you get a difference. This difference and this term. So this is my technical result. A very general formula for TF star T and TFT. And okay, if phi is an analytic function of a neighborhood of this interval, then you can just apply the Helton-Hart formula repeatedly, because this is an algebra, so you can repeatedly use Helton-Hart formula. And for more general function, then you use Fourier transform out of the case of the analytic function. Then in this generality, you are able to show this one. So the main theorem, for the main theorem, you just apply you consider this function. Use this function, then you get this minus df star. This is let's see. Yes, 2 pi I. FT absolute value square minus 1. And FT F prime T over FT in dt. So if you take the limit when beta goes in infinity, then this term disappears. But there might be a 0 here, so you need a principal value in there. So I think my time is up.
But that you have real numbers and index reminds me to the work of Singer, where they had the index with respect to the trace of a type 2 infinity factor. I wonder whether there is some type 2 infinity factor hidden somewhere here. that one can.
I don't know. But of course, you can play the same game in type 2 infinity.
So what's the relation to monotone functions?
So, so this formula is, so when what x to the p over p, then so this formula holds if and only if p, this formula holds if and only if p is larger than or equal to. So the natural question is, so the same, does the same formula hold for small p less than 2? Then actually, so in general, you cannot do it, but if you assume good regularity of f, then you can actually show the same formula for small p. The smaller p is, then you need more better regularity. You need a theory of Bessel space and so on.
You can use the Fredholm index to determine the connected components of the space of Fredholm operators, right? Because it's a continuous function there. Can you use the Witten index also
I
to?
don't know. That's Witten.
No, just a remark, the formula just behind you, in the other blackboard, I think it's famous formula, but I don't remember the name.
I don't have.
Okay.
Yeah.
So it seems I see some relation with second quantization because
Of course.
okay, this is not.
This is a Hilton formula for
This is
the.
the commutator of the second quantized.
So the thing is that this is the Hilton formula for the Hardy space, but when you use so-called Toeplitz quantization, you use Toeplitz operators on the Bergman space, weighted Bergman space. But the Hilton formula itself is the same.
Okay, no more questions. We resume at 10:30.